Hello, everyone. I am delighted to introduce our latest work accepted by CVPR 2024, TransNeXt, Robust Foveal Visual Perception for Vision Transformers. As we all know, the vision transformer has emerged as a popular backbone architecture for various computer vision tasks in recent years. The vision transformer model comprises two key components: the self-attention layer as its token mixer, and the MLP layer as its channel mixer. Self-attention is a powerful feature extraction mechanism that has global information perception and can dynamically generate affinity matrices. In contrast, convolution can only perceive local information and has static affinity matrices, which gives self-attention a strong advantage over convolution operations. The lack of inductive bias is another important feature of the global self-attention mechanism, enabling vision transformers to build powerful data-driven models. On the other hand, convolution operates in a way that is more akin to human vision, allowing advanced convolution models to perform better on small datasets and learn faster. Additionally, self-attention has a significant drawback: its quadratic computational complexity compared to the linear complexity of convolution, which severely limits the application of vision transformer models on high-resolution images. In order to mitigate the computational and memory burdens imposed by the quadratic complexity inherent in the self-attention mechanism, a plethora of sparse attention mechanisms have been proposed in previous studies. One such representative method is local attention, which restricts attention within a window on the feature map. However, due to the limited receptive field, this method often requires alternating stacking with different types of token mixers to achieve cross-window information exchange. Another representative method spatially downsamples the keys and values of attention, such as pooling and grid sampling. This method, due to its sacrifice of the query's fine-grained perception of the feature map, leads to significant performance degradation and therefore also has certain limitations. Recent studies, such as TWINS and MaxFit, have alternately stacked local attention and spatial downsampling attention, achieving commendable performance results. The question is, do these methods of cross-layer information exchange through stacking token mixers really work as well as expected? Our work reveals some new limitations of this approach. Our research observed unnatural visual perception, specifically blocky artifacts, in the effective receptive field of many models. We found these blocky artifacts related to the design of their token mixers and are difficult to eliminate through deep layer stacking. Specifically, SWIN and CSWIN, representative models using local window attention, left unique blocky artifacts in the ERF due to their window partitioning method. Notably, the visualized CSWIN Tiny stacked 21 blocks in Stage 3, yet blocky artifacts in the RF of its Stage 3 output remain significant. This indicates that even with deep stacking, the cross-window information exchange through stacking does not achieve sufficient information mixing for natural visual perception. In more ERF visualizations, we further confirmed the prevalence of these artifacts in various backbone models. For example, in pure convolution models like ConvNeXt, the static convolution kernels operating in a sliding window manner also produced blocky artifacts. Focal Transformer, inspired by biological vision, designed a special window partitioning method, yet it still generated significant blocky artifacts. MaxFit, using a structure that alternately concatenates convolution blocks, local window attention, and grid sampling attention, produced additional grid artifacts besides blocky artifacts. In summary, first, we observed that the boundaries of local operators, such as local attention and convolution, easily form blocky artifacts in the ERF after stacking, and these are difficult to eliminate by stacking deeper layers. Second, translational equivariance is very important. Focal Transformer designed a global attention system that pools progressively from outside to inside, but it did not treat every query equally. Queries at the window edges could not finally perceive neighboring regions outside the window, forming implicit boundaries that led to blocky artifacts. Third, the pattern of artifacts is closely related to the design of the token mixer, with MaxFit's grid attention producing additional grid artifacts. So how can we eliminate these blocky artifacts? Using global attention to remove the boundaries of local operators seems like a good idea, but applying global self-attention at all stages of a hierarchical backbone is too expensive. Using global self-attention in lower stages, like stage 1 and 2, would cause severe memory usage and computational complexity. Some might wonder if the widely used vanilla vision transformers can solve the artifact problem. Unfortunately, standard vision transformers need patch embedding to downsample the image by 1/16, which is essentially a large local operator, resulting in even more severe blocky artifacts than hierarchical backbones. On the other hand, images have strong local priors that benefit the performance of tasks, such as classification. Fortunately, biological vision has already provided a near-perfect solution to this problem. To understand this, we need to know how human vision works. The human visual system is characterized by a dichotomy between foveal and peripheral vision. The foveal vision, covering only 1 to 2 degrees of the central field of view, is optimized for high sensitivity, while the peripheral vision, with a much larger receptive field, is optimized for a broad field of view. This dichotomy suggests that humans primarily utilize peripheral vision for object localization and navigation, but lack precision in detail. To compensate for this, the human eye executes rapid movements, known as saccades, allowing for the processing of information from multiple fields of view and the subsequent integration of this information. Recent research on biological vision from Germany suggests that when superior foveal vision information is available, the human brain does not simply discard peripheral vision information, but compares the inputs from both, weighing their relative reliability to complete the integration of information. This process is a highly complex computation known as transsaccadic perception. It is not difficult to notice that the characteristics of biological vision can perfectly match the needs for artifact elimination and satisfy the priors of image tasks. First, peripheral vision can obtain coarse-grained, almost global perception, which means human vision is not a simple local operator. Second, the human eye can execute continuous rapid movements to integrate information, and in this process, it treats every pixel equally, possessing perfect translational equivariance. Third, the precise perception of human foveal vision can perfectly match the local priors of the image. Fourth, the human brain weighs the relative reliability between foveal and peripheral vision to complete the integration of information. This means that transsaccadic perception is not a static weight combination, but more akin to a dynamic weighting mechanism, similar to an attention mechanism. So, can a token mixer highly aligned with human vision eliminate artifacts? Our research answers this question. We propose a token mixer highly aligned with human vision, named pixel-focused attention. We successfully eliminated blocky artifacts in the ERF from stages 1 to 3 of the hierarchical backbone using this bionic design. Our design simulates the fine perception of foveal vision and the coarse-grained perception of peripheral vision. Our design can match the local priors of the image, possessing priors comparable to convolution while giving each token on the feature map a global receptive field. Our pixel-focused attention uses a dual-path design to simulate the foveal and peripheral vision of the human eye. In one path, we use query-centered sliding window attention to simulate the fine perception of foveal vision and the continuous movement of the eyeball. In the other path, we use pooling attention to simulate the coarse-grained perception of peripheral vision. Remember how the human brain integrates information from both visions? Right. It weighs the relative reliability between foveal and peripheral vision to complete the integration of information. This means that simply adding the results of two attention mechanisms cannot simulate transsaccadic perception because it cannot dynamically measure the correlation of features in the two paths. Therefore, to induce coupling between the two attention paths, we compute the importance in the same softmax for the query key similarity results of both paths. This results in a competition between fine-grained and coarse-grained features, transforming pixel-focused attention into a multi-scale attention mechanism. We provide the formula expression of pixel-focused attention on the right side of the screen. Notably, due to the use of query-centered sliding window attention and the pooling path features shared by all queries, pixel-focused attention has pixel-wise translational equivariance. In order to utilize the linear complexity mode of PFA for large-scale image inference in subsequent applications, we employ parameter-free adaptive average pooling for downsampling in the spatial dimension. However, the average pooling operator significantly loses information. Therefore, we use a single-layer neural network for projection and activation before feature map pooling to compress and extract useful information in advance, thereby improving the information compression rate after downsampling. After pooling, we once again use layer normalization to normalize the output to ensure variance consistency. The downsampling operator we propose is named Activate and Pool. We replaced the downsampling module in PVTV2-LI with our Activate and Pool mechanism and designed a 2M-sized model for ablation experiments on CFAR 100. Our module improved the top 1 accuracy of PVTV2-LI from 68.1% to 70.4%, demonstrating the effectiveness of this approach. Pixel-focused attention also has a mathematically more concise equivalent form. However, due to the need to concatenate the key and value of the two paths, resulting in two large temporary tensors, it causes significant memory usage and memory access pressure, severely slowing down the model speed. Therefore, we did not adopt this form and used the former form instead. Now we have successfully implemented foveal and peripheral vision within a single token mixer. So what measures can we take to further enhance the token mixer's feature extraction capabilities? We have noticed that so far, some non-QKV attention variants have been applied. Replacing the traditional QKV attention's queries and keys with learnable vectors has been used in recent years. For instance, several vision language models utilize queries originating from the textual modality to perform cross-attention on keys derived from the visual modality, thereby achieving cross-modal information aggregation to complete visual question-answering tasks. Moreover, incorporating and optimizing learnable prefix query tokens during fine-tuning has proven effective and efficient. A natural extension of this idea is to incorporate these learnable query tokens into the attention mechanism. For example, BLIP2's QFormer module uses learnable queries to perform cross-attention on visual features, achieving cross-modal feature extraction. Q&A has demonstrated the effectiveness of this method in the visual backbone. We categorize this pattern as learnable key value attention, abbreviated as LKV attention. Similar to LKV attention, there is another non-QV attention variant that uses a set of learnable keys interacting with queries from the input to obtain attention weights, known as Query Learnable Value Attention, abbreviated as QLV attention. This method differs from traditional QKV attention as it disrupts the one-to-one correspondence between keys and values, resulting in learning more implicit relative positional information for the current query. Consequently, it is often employed in conjunction with a sliding window approach. This method was first proposed by synthesizer and language models, and later applied to the visual domain by works like Involution and Volo. We noticed that unlike static convolutions, this method can generate dynamic affinity matrices related to the current query, showing stronger robustness. We discovered that pixel-focused attention can integrate these two attention patterns with minimal additional overhead. We found that adding a learnable query embedding to all query tokens in traditional QKV attention can achieve similar information aggregation effects to LKV attention with negligible additional overhead. We only need to modify equation 1 as shown in the figure. To integrate QLV attention into pixel-focused attention, we introduce a set of learnable tokens in each attention head, allowing these tokens to interact with queries to obtain additional dynamic position bias and add it to the sliding window attention's weights. This enhancement requires only an additional computational overhead of HWK²C. We only need to modify equation 4 as shown in the figure. Additionally, we propose length-scaled cosine attention to further enhance the attention mechanism's ability to handle variable length inputs. Recent research has found that scaled cosine attention, which generates more moderate attention weights, can effectively enhance the training stability of large visual models. However, as the length of the input sequence increases, the confidence of the attention output decreases. Therefore, the scaling factor of the attention mechanism should be related to the length of the input sequence. Su further proposed that the design of attention should exhibit entropy invariance to facilitate better generalization to unknown lengths. He provided an estimate of the entropy of the scaled dot product attention as shown in the figure. Since scaled cosine attention undergoes L2 normalization, the magnitudes of queries and keys are both 1, successfully eliminating the dimension parameter d in the formula. To maintain entropy invariance and disregard constant terms, we propose length-scaled cosine attention as shown in the figure. Here, n denotes the count of effective keys each query interacts with, excluding the count of masked tokens. Specifically, when applied in a transformer decoder, future tokens masked by a causal mask should not be counted in n. By applying the aforementioned diverse attention aggregation methods and techniques for enhancing the extrapolation capability for multi-scale inputs, we propose an enhanced version of pixel-focused attention, termed aggregated pixel-focused attention, abbreviated as aggregated attention. The computational complexities of pixel-focused attention and aggregated attention are shown in the figure. It is noteworthy that when the pooling size is set to a value independent of the input size, both complexities of pixel-focused attention and aggregated attention scale linearly with the length of the input sequence. This implies that both pixel-focused attention and aggregated attention can perform inference in a linear complexity mode. Recent work has observed that incorporating the squeeze-in excitation mechanism into a channel mixer can effectively enhance model robustness. However, the SE mechanism was initially designed to alleviate the issue of insufficient receptive fields in convolutional models. It uses features after global average pooling as the input of the gating branch, achieving a large receptive field for better decision-making, and addressing the problem of insufficient receptive fields in CNN structures. However, in the Vey era, global receptive fields are no longer scarce. This makes the global pooling method used by the SE mechanism show some shortcomings, such as all tokens on the feature map sharing the same gating signal, resulting in coarse-grained channel attention lacking flexibility. We found that simply adding a minimal form of 3x3 depthwise convolution before the activation function of GLU's gating branch can make its structure conform to the design concept of gated channel attention and convert it into a gated channel attention mechanism based on nearest neighbor features. We named this method convolutional glue. This design allows each token to have its unique gating signal while capturing positional information from zero padding, meeting the needs of certain VUTs without positional encoding. These attributes render convolutional glue a simple yet more robust mixer, satisfying the diverse requirements of VUTs. This is the architecture design of TransNeXt. To ensure consistency in subsequent ablation experiments, TransNeXt adopts the same 4-stage hierarchical backbone and overlapping patch embedding as PVTV2. The pooling feature size of the aggregated attention in stages 1-3 is also set to 1/30 of the feature map size. In stage 4, as the feature map size has already reduced to 1/30, we employ a modified version of multi-head self-attention that applies query embedding and length-scaled cosine attention. The specific configurations of TransNeXt variants are shown in the figure. Here are TransNeXt's performance results. Our proposed model sets a new benchmark in ImageNet 1K accuracy and robustness across various scales. Specifically, our TransNeXt micromodel achieves a top 1 accuracy of 82.5% on ImageNet 1K, surpassing the FocalNet TLRF while using 55% fewer parameters. Similarly, our TransNeXt Tiny model achieves a top 1 accuracy of 84.0%, outperforming ConvNeXt B with a 69% reduction in parameters. Remarkably, at a resolution of 384 by 384, our TransNeXt small base model surpasses the larger MaxFit base model by 0.3% and 0.5%, respectively, after only 5 epochs of fine-tuning compared to the 30 epochs used by MaxFit base. In terms of robustness, our model shows superior performance on 5 additional test sets. Notably, on the most challenging ImageNet A test set, TransNeXt demonstrates a significant advantage in robustness as the model scales up. We used a mask RCNN detection head trained under a 1 schedule to evaluate the performance of ImageNet 1K pre-trained TransNeXt on object detection and instance segmentation on the COCO dataset. Our model demonstrated comprehensive superiority when compared with previous state-of-the-art models. Notably, Even our tiny models surpass the base models of FocalNet, Intern Image, and CSWin in terms of box AP. Similarly, we utilized a dyno detection head, also trained under a one-time schedule, to further assess the potential of our model for object detection. Our TransNeXt tiny model achieved a box AP of 55.1 under a 4-scale setting, surpassing ConvNeXt L by 1.7 with only 14% of the latter's backbone parameters. We used UpperNet and mask deformer methods to train the ImageNet 1K pre-trained TransNeXt at a resolution of 512 by 12 for 160K iterations and evaluated its semantic segmentation performance on 8020K. Our TransNeXt demonstrated comprehensive superiority over previous methods across all sizes. Our TransNeXt base even surpassed ConvNeXt B, which was pre-trained on ImageNet 22K and further trained at a resolution of 640 by 640. These results indicate that our method has the potential to transcend model size limitations and break through data volume barriers. In summary, our model demonstrates a more pronounced performance advantage in dense prediction tasks compared to classification tasks. We believe this validates the effectiveness of the biomimetic vision design of aggregated attention, which enables a more natural visual perception at earlier stages compared to previous methods. We also tested TransNeXt's multi-scale inference performance and reported the performance results in both normal mode and linear complexity mode. During inference, TransNeXt in normal mode sets pool size to 1/30th of the input size, while in linear mode, these are fixed at 7 by 7. As shown in the figure, TransNeXt outperforms pure convolutional solutions in both normal and linear modes. Large convolutional kernel schemes, such as RepLKNet and SLAC, also proposed to address depth degradation, exhibit significant performance decline during large image size inference. This reveals the advantage of our approach over large kernel schemes in addressing this issue. For instance, RepLKNet 31B only achieves 0.9% accuracy at a resolution of 640 by 640. Traditionally, pure convolutional models are believed to have better multi-scale applicability than VT models, and such experimental results imply that this opinion needs to be re-examined. The performance decline of large kernel strategies also merits further investigation by the research community. In summary, our contributions are as follows. 1. We propose pixel focused attention, a token mixer that closely aligns with biological foveal vision and mitigates potential model depth degradation. This novel attention mechanism works on a per-pixel basis, effectively simulating the continuous movement of the eyeball and highly aligning with the focal perception mode of biological vision. It possesses visual priors comparable to convolution. 2. We propose aggregated attention, an enhanced version of pixel-focused attention, which further incorporates two types of non-QKV attention mechanisms into pixel-focused attention. Notably, we propose a highly efficient approach within this framework, with the additional computational overhead accounting for a mere 0.2 to 0.3% of the entire model, leading to an exceptionally cost-effective unification of QKV attention, LKV attention, and QLV attention within a single mixer layer. 3. We propose length-scaled cosine attention that enhances the extrapolation capability of existing attention mechanisms for multi-scale input. This allows TransNeXt to achieve superior large-scale image extrapolation performance compared to pure convolutional networks. 4. We propose convolutional GLU, which incorporates channel attention based on nearest neighbor image features. Compared to convolutional feed-forward, it realizes the attentionalization of the channel mixer with fewer flops, thereby effectively enhancing the model's robustness. We introduced TransNeXt, a visual backbone that delivers state-of-the-art performance in various visual tasks, such as image classification, object detection, and semantic segmentation among models of similar size. It also exhibits state-of-the-art robustness. Additionally, we are re-evaluating the conventional belief of superior multi-scale adaptability in CNNs over VUTs. Our research found that existing large kernel CNNs exhibit drastic performance degradation in multi-scale inference. We believe this finding will inspire the research community. We have provided more ablation experiment data and visualization results in our paper. If you're interested, please read our paper. Thank you for watching.